Hello friends, welcome back to my channel. Today's topic is heat rectification via graphene nanomesh. One of humans' dreams is to be able to control heat transmission as precisely as we can control electrical current. However, there is still a need for a high-performance thermal rectifier or thermal diode. Researchers from the Japan Advanced Institute of Science and Technology have recently produced a promising asymmetric graphene nanomesh device with a high thermal rectification ratio at low temperatures. The work serves as a blueprint for creating a high-efficiency thermal rectifier based on graphene nanomesh structure. Star-C developed the thermal rectifier for the first time in 1936, in which the heat flux from one direction is greater than the opposite way, analogous to an electrical diode. The traditional bulk material mechanism is based on the thermal conductivities of two different composition materials with differing temperature dependencies. However, the majority of the outcomes based on this technique have a low rectification ratio of around 10% to 20%. Furthermore, knowing the thermal conductivities of each portion of a thermal rectifier in nanoscale devices is very impossible. A fresh technique for developing a high-performance thermal rectifier is urgently needed in this situation. So, these research findings have shown that the thermal rectification phenomenon can be observed at low temperatures with a high ratio of up to 60% on suspended asymmetric graphene nanomesh devices, 150K and 250K. They use graphene nanomesh as an artificial phononic crystal structure on half of the heat flux channel's area. Device fabrication. The device was fabricated using advanced graphene nano-electromechanical systems and helium-ion beam milling techniques. A 500 nanometers long, 1.2 m wide suspended graphene ribbon is in the center. A gold nanowire is connected to each side of the graphene ribbon, and its resistance can be precisely measured using a 4-probe measurement setting. The fabrication of asymmetric graphene nanomesh devices began with the transfer of chemical vapor-deposited graphene to a SiO2 Si substrate. To achieve good adhesion with the substrate, the first electrode layer was patterned. Before deposition of the metal layers, the graphene beneath was removed using reactive ion etching. The second electrode layer was then used to ensure that the first electrode layer and graphene were in good contact. The graphene ribbon was created using electron beam lithography, hydrogen sil sesquioxane patterning, and plasma etching. After dipping into buffered hydrofluoric acid, the graphene ribbon was suspended. They successfully observed the thermal rectification on suspended graphene devices at both 150 and 250 Kelvin. The nanopore diameter is about 6 nanometers, and the pitch is about 20 nanometers. Heat flux measurement is not disturbed by the leakage of electron current through the suspended channel when using the differential thermal leakage method. Thank you for watching this video tutorial. If you like this tutorial, please share with your friends and colleagues. Thank you.